Log on, tune in, find out. Another good idea from Cambridge.
In group theory, so it's a kind of zoology, but which will perhaps suggest that there is a very large and very interesting mathematical being behind. So this is joint work with Gunther Mahle and Jean-Michel. And since you will hear sometimes the strange word spets, I just want to explain what spets is. It was initiated in the Greek island named Spetses in '93, and this is a touristic advertisement for the Spetses island. So I want to start with something which is quite familiar to a lot of people in this audience. One of the tables which you can find in Roger Carter's book and especially in George Lustig's book. So this is the unipotent characters for the finite reductive group over FQ of type G2. So G2 is the Dintine diagram is there. Everyone knows G2 here in the audience. And here is the kind of table you find in Lustig's book. That needs some explanation, which will be given all along this lecture. But at least you can see, if you don't know what family or eigenvalue is or fake degree is, at least, and this first strange column, at least here what you have is the list of character degrees, of unipotent character degrees for the group G2 of Q. So these character degrees are always of the shape a power of Q and then a bunch of cyclotomic polynomials, and they are written that way. If you look at Carter's books, they all look the same. And you have some denominators also. They are not polynomial in Z, they are polynomial in Q. And these denominators precisely are made of bad prime numbers for the Weyl group you consider. This is a kind of general rule for all the character values of G2. And now I turn to a stranger object. Let me consider the complex reflection group G4. G4 is the smallest of the exceptional groups which were classified by Shepard and Todd in the 50s. It's a group generated by two elements of order 3. This is the diagram over there, S and T, which satisfy the same Bragg relation as A2, namely STS equals TST. And this strange explanation in bracket G4 is 2 times S3 means essentially that all the invariant of G4 are twice the invariant of S3. The invariant degrees, the co-degrees, the order of the center, etc. So if you know this, you know that the order of G4 is 4 times the order of F3, so you have enough information about G4. And now comes roughly the same table, except that you always have this strange column, which I will explain, and also fake degrees, eigenvalue, families, and character degrees. But the character degrees now are no more polynomials over Q. They do have denominators, but there are no more polynomials over Q. There are polynomials over Q of zeta 3, the third root of unity. Apart from that, they share the same properties, which I want to explain at least for part of them, as the one of G2. So let me start to explain a little bit what are they. But before doing that, I need to give a very short crash course about the characters of finite reductive groups. So let me consider bold G be a reductive group over FQ bar, and all this Frobenius endomorphism. And just for simplicity of this lecture, we assume that the group is split. And unbolding letters means taking the fixed point by the Frobenius endomorphism, so taking the finite groups. Now, the G conjugacy class is the conjugacy class under the finite group, so according to what I said, of F stable maximal tori in the maximal groups, or in bijection, in natural bijection, with the conjugacy classes of the Weyl group. So for each, for an element in the Weyl group, I may speak of the torus TW for W in the Weyl group, and this is one of the tori up to G conjugation concerned with this element TW. That's why I introduced this. Now, the set of unipotent characters, I try to make the notation as explicit as possible. It's always a problem. the set of unipotent characters are just the set of irreducible constituents of the Deligne-Lustig induced character from TW up to G of 1. So this Deligne induced character is an alternating virtual character constructed as the using the cohomology of the Deligne-Lustig variety. I'll come back to this notation later on, but I consider that this is more or less known in this audience. Now, the unipotent character sheaves of for all W is yes. Sorry for that. Yeah. The unipotent characters are those for which there exists a W such that it occurs in RTW. Now, the unipotent character sheaves, I will say even less. It's just another C basis for the space of class function generated by the set of unipotent characters. Another C basis. That's all what I want to use here. Now, there is the Lustig Fourier matrix, S, which is the matrix which takes one of these bases, the unipotent character sheaves, up to the unipotent characters. This is essentially what Lustig gives in his huge book. And finally, this Lustig matrix falls into blocks, and these blocks are called the Lustig families of unipotent characters. All right? Let me tell you that Lustig gave this whole datum for any type of finite reductive group, the character, the unipotent character, the character of sheaves, the Fourier matrix, etc., and the blocks, by a case-by-case analysis. There is no general theory behind the scene explaining why this datum has the property, some of the properties I'm going to quote now. All right? So here, for example, is the Lustig matrix for G2. And you'll see that the Lustig matrix is almost integral. Once again, the denominators here are the bad primes. And of course, it has blocks. So let me delete the zeros. So you see that it has two blocks, two families. All right? So here you see that explains a little bit of my table. You have two families, one denoted C1 and the other one denoted S3. In C1 is denoted S3. Don't ask why, and even don't criticize the notation. In all these areas, notation is sometimes terrible, but we have to stick to this to be understood. Okay, now this is the Fourier matrix for G4. Of course, you are well aware that there is no reductive group of Weil group G4 or a field with Q element. Nevertheless, there is a Fourier matrix. It's also a Fourier matrix by blocks. So you count 4 blocks, 1, 2, 3, 4, and that explains a little bit of the notation on the table. You see 4 blocks, C1, X3, and another C1 and X5. So these are the blocks. Okay. Now, in order to explain the notation on the first column, I want to say a little bit about Harish-Chandra series, because the notation of the first column is taken from the Harish-Chandra theory, the ordinary Harish-Chandra theory, because there is also a generalized Harish-Chandra theory which will come into the picture. But let me just very quickly explain the Harish-Chandra theories. A Levy subgroup of an F-stable parabolic subgroup of G, I'm still sticking with the reductive group defined over FQ, etc. A Levy subgroup of an F-stable parabolic subgroup P of G is called here a one Levy subgroup, one meaning that it is contained in the parabolic subgroup. So it gives rise to this picture. This picture is written above in the algebraic group. And since P is F-stable, everything is F-stable, so you can put an F everywhere, and you have the similar picture in the finite group. And so then it gives rise to the Harish-Chandra induction, ordinary induction. It goes from take an L module, view it as a P module, and then induce it up. And the adjoint functor, as well as I'm working with in the semi-simple cases, the adjoint functor is the Harish-Chandra restriction, and the Harish-Chandra restriction consists in taking a G module and you take the fixed point by Vf, and you get an L module. All right, well known. And one of the properties is that this construction does not depend on the choice of P. Of course, for a given L, we have several P's, but this functor doesn't depend, naturally, in the natural sense, doesn't depend on the choice of P. All right. Now comes the main tool of Harry-Chandra theory. First of all, we say that the character is cuspidal if the Harry-Chandra induced is 0 for whenever you take a proper Levy subgroup. So what is written here, whenever L is a proper Levy subgroup, then the Harry-Chandra induced is 0. In other words, whenever you take a unipotent radical of a parabolic subgroup, then the set of fixed points is 0. And then, just for convenience of notation, a pair L lambda, where L is a one Levy subgroup, and lambda is a character of L, is the pair itself is called one cuspidal if L is a one Levy subgroup, and if lambda is a cuspidal character. Now, there is the main theorem due to Harry-Chandra, well known, well used in many areas of mathematics. First of all, the Harry-Chandra induction starting from the cuspidal pairs determines a partition into the set of irreducible characters upstairs. So they are like this. They are partitioned. And of course, you take the L lambda up to G conjugation, and so it's a classification of the set of irreducible characters of G over, say, field of complex number. This is the disjunct union of the set of irreducible constituents of this induced, Harry-Chandra induced from L to lambda. All right, first of all. Secondly, the group which locally controls that, namely the normalizer of a pair divided by L, is always a finite Coxeter group. There is no known general reason for that, except case-by-case analysis. It's always a finite Coxeter group, a finite. I mean, a finite which doesn't depend on Q. It's something which is computable in terms of the while group, period. Not computable. Q has nothing to do. It's controlled by a true finite, what I call a true finite group, which doesn't depend on Q, all right? And no, in my case it is crystallographic, but if the group is not split, then you can find some. And then what is much better in a sense is that the commuting algebra of this induced module, whose constituents are there, the commuting algebra is a Hecke algebra for this finite Coxeter group. I will come back to this notion. So that means that, of course, you know the constituent of this module are in bijection with the characters of this Hecke algebra, which are in turn in bijection with the characters of this finite Coxeter group. So in a sense, you see, when you expand, when you consider this partition of the set of irreducible characters classified by all the L lambda, each of the set of irreducible characters is in natural bijection with the set of characters of a finite Coxeter group. So it's a kind of skeleton, which in a sense doesn't depend on Q of the set of irreducible characters of G. Very well. That's well known, and that's been known for a long time. This fact here is essentially due to Lustig again, and also Lehrer and Howlett, and well, lots of things are due to Lustig in this area. Anyway. Very well. So this is the first, the old approach of Harry-Chandra theory. So keep this in mind because I will come back to the tables later on. Now I have something else to explain about the tables. First of all, the degrees. The starting point is that the set of unipotent characters and the set of unipotent character sheaves are actually parametrized by sets which are independent of Q. The trivial example, but too trivial, but still the trivial example is the case of GLN, where the set of unipotent characters is parametrized by the set of partitions of N. And partitions of N do not involve Q, of course. So first of all, the set of unipotent characters and unipotent character sheaves do not depend on Q. They depend only on the type of G, which I will come back to. The degrees now of these characters, or this class function, the value in 1, in other words, are polynomial, depending only on the type and on the set, evaluated at Q. This has been known for a very long time, also for finite reductive group. Now, among the unipotent character sheaves are these functions here. It's a nice linear combination of the Deligne-Lustig induced indexed by the characters, I should have said, by where chi is a character of the value group. You see that because I compute chi of W. So among the characters, among the unipotent character shifts are these functions which are labeled by the characters of the value group. Okay? And now if you compute its degree, namely the value of this class function at 1, you find what is called the fake degree, which is the multiplicity of chi in the co-invariant algebra of W. I don't want to be too technical, but I just quote it to show you how this geometrical object, the unipotent character shift, the degree, etc., can be computed in purely combinatorial terms using the value group. They are the graded multiplicity of chi in the co-invariant of W. So remember, we have degrees, we have Harish-Chandra degrees, these fake degrees, and finally the degrees of the irreducible constituent of our LG of lambda in this Harish-Chandra theory are given by the generic degrees of the Hecke algebra. You know that the Hecke algebra have a generic version and they have generic parameters, generic invariants, generic meaning that their polynomial is Q, and so they're computed by this mean. And finally, this is also a consequence of Lustig work, the Fourier matrix. The Fourier matrix is the matrix linking the unipotent character and the unipotent character shifts is independent of Q. You saw it. There were matrices in. So now we have more explanation. Can you see that there is some red? Strange. There is red on my screen, but oh, sorry. Let me see. You see red? No, you don't. Oh, I'm sorry. Maybe if I put it some more, if you hear me, put more contrast, you'll see red. Because what I want to say is that this notation here now is of the character. These tables concern unipotent characters of the group of type G2 over the field with Q element, all right? So this column classifies this character according to ordinary Harish-Chandra theory. And ordinary Harish-Chandra theory means that they all live above a cuspidal pair. So these are cuspidal pairs in themselves. These are cuspidal characters of G2, this is here. And the first 6 characters are the characters of the principal series. And they are labeled, this strange labeling, 1, 3, 2, 2, etc., is the labeling of what? The characters of the principal series are in bijection with this Hecke algebra, which is in turn in bijection with the irreducible characters of the Weil group. So they are in bijection with the characters of G2 as a Weil group. And the character of G2 as a Weil group are labeled usually by this kind of symbols. It comes from the Lustig by symbols, etc. So these explain, in a sense, how they are labeled on this left column. And red was here to show you that in red, it was up to here, the principal series, and these are cuspidals. Now, the degrees, I've explained the degree, why there are degrees which are given by polynomials. But what is more interesting is, except that, I'm really sorry, all the magic of Beamer is lost, because I put in blue and red the different Harish-Chandra series for G4, whatever it means.
We can just about see it. Yeah.
Okay, so you should, everyone should go to the bottom. So here, in this case, the G4, the machinery behind G4, I don't know what to say because there is no finite reductive group, but the machinery behind G4 has several, this time, Harish-Chandra series. First of all, there is the principal series, which are here and here. They are in red. Now, that means that these characters are in bijection with the character of the Weil group itself.
Could you say the character of what group? No group at all?
Depending. These characters are characters really of the Weil, these 5.
Right.
Yes. These are just datum, organized in a way which is absolutely identical to the way characters of the reductive groups are organized. For example, there are also 2 there is also an L lambda series. This is ZC3. This is the cyclic group of the 3. The cyclic group of the 3, of course, is a parabolic subgroup of G4. You see G4 as it has
No,
two.
I'm asking, did you just made them up to look nice like the previous ones, or do they really are characters of something?
No, these are not characters. These are polynomials. But the point is that they are organized, and we'll see when I go up they are organized in a combinatorics which is quite analogous to the combinatorics of the finite reductive group. And of course I can cook them up, but the final result is that there is a unique solution. So of course, but all right. So what did I say? The G4, the G4 has two parabolic subgroups in the ordinary sense of parabolic subgroup of reductive group, which are three essentially, one and this and three type G4 itself, and you see the two parabolics are got by the. So one of the parabolics is C3. So this corresponds to that and to the Arichandra series. And this the relative value group, remember the group I said it is a Coxeter group always. In that case, it is a group of order 2. It has two characters, so it parametrizes these two characters. Now already at that point, you know that I could not cook them up because there are some conditions. For example, let me go back to the true table of characters for G2. The characters of the principal series are characterized by the fact, the character degrees of the principal series are characterized by the fact that they are not divisible by the first cyclotomic polynomial. In other words, they take a value at 1 which is different from 0. And so you just compute the number of characters and you find these characters have to be in bijection with the characters of G2. Now, in that case, it's the same. The characters of a principal series, which you would see if they were in red, you see that the characters of the principal series, the first three ones and these ones here, are those which are not divisible by phi1. This is the first condition, but we can go. Now, I didn't say anything about eigenvalues of Frobenius. What are they? Remember that was this column eigenvalues of Frobenius. So let me quickly remind you what they are. These are TWG of 1, I'm sorry, it's in the little g is 1. This induced character of the linguistic character is just by definition the alternating sum of the trace. No, it's this. The character RTWG, I'm missing one. I should have said RTWG of 1 of G. This is what should be written on the black hole. The value at G of this character is the alternative sum of the trace of G acting on the ith group of compact support L-adic cohomology of the linguistic variety XW. And each of these compact support cohomology group is acting on by G because G acts on the linguistic variety, but also by the Frobenius on the other side in the sense. It's a module for the product. And so for any unipotent character rho, the eigenvalue on F on the rho isotypic part of have to be considered. And they have the following property. They are all always of the shape lambda rho times q to the n over 2, where lambda rho is a root of unity, n is an integer, so it's a half power of q. It's always like this. But more or less, this lambda rho here, this lambda rho which is independent of I and W. This is also one of the properties of the Dolin-Lutzig induction. In other words, it doesn't depend on I, it doesn't depend on W, it depends only on the unipotent character. So in other words, for any unipotent characters is attached a root of unity, this lambda rho, and which is called the eigenvalue of Frobenius attached to this unipotent character. And in the table, I gave you the list of eigenvalues of Frobenius attached to the list of unipotent characters. Now, let me try to explain before giving more axioms, more properties of these tables, let me try to explain how you can construct this simply, and how finally Lustig did this, simply from the datum of the while loop. And of course you have explanation, geometrical explanation in terms of the algebraic group, but how can you build this up simply from the while loop? Well, by the isogeny theorem, GF is determined by its reflection datum, which is essentially the root system, the X, the Y, and the root system and its dual, and the choice of Q. It's what determines the group. The point is that all the above data, set of unipotent characters, the degrees, the Fourier matrix, the eigenvalues of Frobenius, the set of unipotent character shifts, etc., depend only, actually not on even on the root, on the reflection datum, they depend only on the tensorization by C of the root datum. They depend only on the underlying vector space, or the above lying vector space on which the group acts, and the action of the group. That's all. The Eck algebra will come later. So we have this. Notice that a group and its dual in this context are not distinguished, because V and V star are the same. So the group, it's a fact which has been noticed case by case, that the group and its Langlands dual have the same order, the same set of unipotent characters, the same set of unipotent character degrees, the same set of Fourier matrices, etc., the same set of Fourier. Sometimes, if people want to think about history of mathematics, it was even a kind of discovery. Lustig gave descriptions of the unipotent characters in terms of combinatorial structure, symbols of that kind for B, all other symbols for C. And it took a while to realize that these symbols were in natural bijection, because C and B, from this point of view, are not distinguishable. Undistinguishable. Okay. Of course, if you start to do this game, starting with the complex reflection group, so I start with the complex reflection group V and try to construct something, then the group and its dual will be distinct as long as the complex reflection group is not real. All right. And one essential ingredient in computing all this Lustig datum from the while loop is the Hecke algebra. The Hecke algebra, you heard many things about Hecke algebra here. It is the the deformation of the algebra of the while loop when you replace you keep the break relation and you replace the condition that S minus 1, S plus 1 is 0, S squared is 1, by this deformation. This is Hecke algebra. And starting from the Hecke algebra, starting from its generic degrees, starting from the datum and computation with Hecke algebra, and from all the set of axioms that you can find in Lustig's work, one can construct everything starting from the while group without building up the reductive group and without the geometrical explanation. So you avoid and you build up the whole thing. And the Spencer's Island is there that we starting this game when we replaced the while group by the complex reflection group, which is the cyclic group of order 3. After all, this is the first non-trivial example of a complex reflection group which is not a while group. And doing this work, what I say, you start with the while group with the suitable Hecke algebra and you start to build up all the machinery. It's quite a work, even for the group, the cyclic group of order 3, and the solution is unique, but it's certainly not trivial. When I say unique, of course, I didn't give you the list of axioms. I will say like Thomson did, I have no time. But well, at this stage you have to believe me. All right. So what were the rules of the games for general complex reflection groups? Hecke algebra. Let me say a few words about what is the situation of Hecke algebra, not only for while group or for reflection group, for Coxeter groups, but for general complex reflection groups. First of all, every complex reflection group has a nice presentation a la Coxeter, as I say. G2 is like this, G4, I described it. And it's true for any complex reflection group. Every complex reflection group has a field of realization, QW. Namely, it has a smaller field, a small Lust field over which all its representations are defined. This is not the usual property of a finite group. There are several minimal fields, but these groups have a small field over which all its representations are defined. This is also a case-by-case analysis, I must say. This area is full of case-by-case analysis, and of course for G2 it's the rational, and for G4 it's exactly the field we already encountered, the extension, the cyclotomy field. The associated generic Hecke algebra is defined as you may think. You keep the braid relation. These are the braid relations for G2. These are the braid relations for G4. And you replace the order relation, S squared is 1, by a general polynomial of order 2. S minus U0, S minus U1 is 0. In case of G4, you replace by a general polynomial of order 3. And you get a deformation which has, a priori, all the chances to be anything.
It's the same for T.
And the same for T. Yeah, and the same for T. Probably it's, no, I have no space. The rules are obvious. You replace, you keep the braid relations, and you replace the order relation by a general polynomial of order T. Well, first of all, what is absolutely marvelous, I'm cheating a little bit because the proof is not yet complete. Some of the exceptionals, I mean maybe 2 or 3, and don't even remember, big exceptional complex coefficient group are still resisting, but view it as a conjecture we believe very strongly. But apart from that, for all the infinite and almost all the exceptional, it's proved that the generic Hecke algebra is free of rank the cardinality of W over the appropriate Laurent polynomial. I just add up the indeterminates, I put it in the relations. So it's a true deformation of the group algebra of the Weil group. Not only that, but it becomes semi-simple over a field obtained by extracting suitable roots of the indeterminates. This is also known in all but maybe 3 cases, and in conjecture, and there are strong indication that it is true. And of course, now, by a suitable choice, by what is known in this area as Tits deformation theorem, because this is a deformation, then there is a bijection between the set of irreducible characters of W and the set of irreducible characters of this Hecke algebra. This is general. Now what is even stronger is that it becomes equipped with a nice symmetrizing form, a linear form, which makes it a symmetric algebra over this Laurent polynomial. And this form, well, I don't have time, and this is not the place to give lots of conditions about this form, which is unique, subject to certain conditions, and which is strongly linked with the what's happening at the level of the braid group. Because of course, behind the scene, you have the braid group. When you keep the braid relations, that means that this algebra is an image of the algebra of the group algebra of the braid group, and the property of this form are better expressed in terms of the braid group. Anyway. And finally, like it is in any symmetric algebra, this canonical symmetrizing form is decomposed into the set of irreducible characters. Remember that the set of irreducible characters are in bijection with the set of irreducible characters of the complex rotation group, and the coefficients are 1 over S chi.
Wait.
Yes?
What do you call a form? Is that a linear form?
A linear form, yes, yeah, a linear form which makes it a symmetric algebra, this form, yeah. This is what I call a symmetrizing form. So this symmetrizing form is decomposed into the set of irreducible characters, and the coefficient, because it's like this, it's very easy to see, this is 1 over S key, where the S key is an element of the Laurent polynomial, which is underlying the situation for some. I must say that the knowledge, what I'm saying here about complex function group, of course, works for Weil groups or for quotient groups, and so the knowledge of these elements, which are called the Schur elements, is quite useful even for Weil groups. These are polynomials, but they have also coefficients in front. They are not monic polynomial, or they have some coefficients. They are divisible by some primes, which are the really bad primes for the group. The bad primes can be computed in here. The real bad, but I have no time for speaking about bad ones. Okay. Now, with which algebra did we start to work, do all the game? We concocted this strange name Spatial for the reason I explained. So the Spatial Hecke algebra is the specialization of the Hecke algebra defined as follows. Suppose that our group is generated by a pseudo-reflection of order D, a pseudo-reflection of order T linked by a name-break relation, meaning ST, 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 etc. m times equals T, ST, ST, S m times. This is the meaning of the relation. Suppose that. Now, the Hecke algebra is a specialization of the generic, so we have to specialize the UIs, which are here. We have a polynomial of order D replacing the order D relation. And it's this one. We decide that this is this one. S minus Q plus the remainder. Let me notice two things. First of all, if you put Q to be 1, you find the group algebra. So it's a deformation of the group algebra. And in our cases, of course, for G2 and for any Weil group, you find the usual Hecke algebra, which is used with the principal series. For a non-Weil group, you find another algebra, which in the case of G4 is this one, and the recipe is rather clear. And starting with this Hecke algebra, we want to compute the character degrees, Frobenius eigenvalues, etc., subject to lots of axioms, which I didn't quote, or I just quoted some of them. The point is that it doesn't work for all complex reflection groups. And what doesn't work? The first condition is this one. If you start with the Weil group, let me call PWQ the Poincaré polynomial of the Weil group. Then this part, Q to the n, Q minus 1 to the r times the Poincaré polynomial, is the order of the corresponding reductive group by Steinberg's formula. And it happens that when you divide this by the sure elements, which I defined just before, you find what the degree of the corresponding character. Remember, the Hecke algebra has to do with the principal series. So the principal series, you find some of the unipotent characters. These unipotent characters have degrees, and this is the recipe in Lustig theory to compute the degree of the corresponding character corresponding to this character of the Hecke algebra. And so this has to be a polynomial. So start with at least for the Weil group, this is a polynomial. So start with the complex reflection group and impose that this is a polynomial in Q. Then you find some of the complex reflection group, and here is the list. Here's the list of the spatial group. A group is spatial if you have this condition. No, wait a minute. Among the imprimitive one for the infinite series, you see the infinite series according to Shepard-Todd notation is of the shape G of D times E times E and R. R is being the rank. So it's an infinite series. So I just keep the one for which E is 1 or for D is 1. And only those are the special ones. And among the exceptional ones, that's terrible because they are in red. So if you can see, I can read them for you. The 4, the 6, the 8, the 14, 23, 24, 25, 26, 27, quite a lot in large dimension, 28, 29, 30, and the last ones. Of course, some of them are obviously spatial, the Weil groups. So I pointed out the Weil groups, which are obviously spatial. But this one, and that one is not spatial, and the G4 is not are not Weil, and this one is not Weil, but it's spatial. It shares this condition. And the point is that for these groups, we can rebuild, in a sense, all of Lustig datum, which I'm going to go on describing now. Let me say that we have no explanation whatsoever about what these group, why these groups are so spatial, but they are. Just one remark. For a complex reflection group, irreducible complex reflection group in dimension R. It can be generated by R generator, like Weil and Cox groups, or some of them cannot, and then you need R+1 generators. None of these Bedley generated groups occur as spatial group. So all our spatial group are well generated, namely generated by R generator. You follow me? But there are well generated subgroups which are not spatial. So what is behind spatial, I don't know, but I want to say even at that point that there is something which has to be understood. There is an object behind. There is something which can be built in a sense analogously to the way reductive groups are built out of Weil groups, because the amount of datum is now unbelievable. Let me go on. Let me go on with the ordinary theory of a finite group. Harish-Chandra theory can be generalized. Let me give you just a simplified version of this generalization. So back to the context of a finite reductive group with a Weil group W. And choose a zeta regular element. What's that? It's an element which has an eigenvector attached to the eigenvalue zeta. Zeta is a root of unity, which doesn't live in any of the reflecting hyperplane, which is the set of regular points of the space of representation. So the element is called regular if the corresponding eigenspace is maximal among what? I know that you are it's maximal about all the possible. It's maximal when W varies. So it's maximal among all.
Zeta is given or
Zeta is given. Zeta is given. Zeta is given.
for every.
So for a given zeta, I choose a zeta regular element, meaning that its zeta eigenspace is maximal among the eigenspace of the element of W. Of course, it's not always the case that there exists a zeta regular element. The zeta, the possible zeta which give rise to a regular element have been classified by several people, mainly by Springer. I don't want to enter into this picture. Okay. One of the properties is that the centralizer of a zeta regular element is a complex reflection group. And this is one of the ways where complex reflection groups get out of say, Weil groups, for example. Because if you have a Weil group, you have lots of other Weil groups, Weil subgroups, all the parabolic subgroups are Weil subgroups, but they are all defined over Q. But if you perform this, if you look for the centralizer of a regular element, then you get a group which is a complex reflection group, but an extension of Q. So it's the way you can close the family of complex reflection groups. All right? And it happens also that, now I come back to the context of finite reductive group, there is a torus TW, and the normalizer of the torus divided by TW is isomorphic. It can be computed, as it was the case, remember, in the Harish-Chandra series, I told you that the corresponding subgroup is computable in Coxeter terms. It's a true finite group. In that case also, it's a true finite group, and this is precisely this complex reflection group. This is one instance of a quite general phenomenon when you replace the L of the Harish-Chandra theory by another class of L's. Instead of working with the one Harish-Chandra series, you work with the D Harish-Chandra series, and you get the same type of thing. You get also that the normalizer are, this time, complex reflection groups, not Coxeter, not Weil, but always true finite groups. It's also another instance. And exactly, well, not exactly, because now it's a conjecture, exactly as it was the case in the Harish-Chandra theory, there is at least a conjecture. No, let me see. There is a zeta cyclotomic algebra for this complex reflection group, which controls this. It's true. What is conjectural is that this cyclotomic algebra is the algebra of the morphism of the entire cohomology of the variety. That is known just in a few cases. But if this were true, if this is true, there are lots of numerical consequences, and the numerical consequences are checked, and so there is indeed a zeta cyclotomic algebra which controls this. What is zeta cyclotomic then? And also the conjecture predicts the eigenvalue of Frobenius attached to the irreducible constituent. Let me just mention in connection with Raphael's talk that all these this type of conjectures were prompted by the Abel and defect group conjecture, which is a conjecture about abstract finite group, which has nothing to do with the algebraic geometry. But in that case, that takes this shape, and that led us to, in a sense, check this for things which are no more groups. So it's a bit strange situation. But I mentioned the cyclotomic Heck algebra. Let me briefly explain what they are. Just by examples. Let me give examples. So for G2, remember the Heck algebra for G2 is generated by S and T, which have the same braid relation, and where the S2 equals 1 relation is replaced by a polynomial. So here is a complete table of the cyclotomic Heck algebra which occur for the regular zeta in the value G2. The possible regular element zeta are 1, -1, zeta 3, and zeta 6. Period. And of course, they are Galois conjugates. In that case, they are centralizers. Their centralizers are complex reflection group. Yes, indeed. The centralizer of 1 and 1 was in G2, and the centralizer of the zeta 3 regular element is C6. So you see, you get out of the class of value group. And that thing. It's the cyclic group of the 6.
I saw the type C.
No. Oh, yes, sorry, yes. Yes, it's bad. Yeah, it's bad. It's bad notation, I agree. It's Z over 6Z. Sorry. But of course, it cannot be a group of that large rank, but still. Okay, all right. So one has to find now a Heck algebra for this course. Let me concentrate on C6, for example. So the would-be value group, the complex reflection group now is C6. You have to find a Heck algebra for this C6. So that means that you have to find a polynomial of order 6 which deform the S6 is 1 in such a way that if you choose Q to be zeta 3, you find the algebra of a C6. You see the rule of the game. This is a zeta 3 cyclotomic Heck algebra, a deformation of the group such that when you put Q to the zeta 3, you recover the group algebra. You can check that it works. I mean, if you, in each of these cases, in the third row, if you put Q to be zeta 3, it's an exercise. I checked it before my talk. So you find the group algebra of C6. And now, well, everything works for G4. This is the list of regular possible zeta for G4. This is the list of their centralizer, G4, and cyclic 6, cyclic 4, cyclic. And for each of these groups, you have one and only one solution, a Heck algebra, whose parameters make them a zeta cyclotomic algebra, but which controls the Linus-Stick induction. And let me explain how it is on the can be seen on the table. And let me just show you what happens on the table of G4, because it's much more interesting than the table of G2. But you believe me that of course it works for G2. In red, so let me ignore the red since you didn't see it, but you don't see it. But let me concentrate then on the green bullet. The green bullet is the 5-4 series. What does it mean? That means that zeta 4, I, is regular for G4. All right. So there is a kind of equivalent of the 4 Arichandra series, zeta 4 Arichandra series, which can be seen on the table because exactly as the case in the ordinary Arichandra series, it corresponds to characters which do not vanish at the value zeta 4. So in a sense, we are not divisible by 5-4. So if you look at this table, you pick the characters which are not divisible by 5-4. You must find how many characters must you find? You must find how many characters as the corresponding centralizer of the regular element in G4 as characters, namely 4. You find 4 characters. And now their degrees should be computable in terms of the corresponding cyclotomic Heck algebra. I gave you it here. So we have the cyclotomic Heck algebra, everything is fixed. It gives you the generic degrees, and the generic degrees should give you exactly those 4 characters. And everything is true, so this table can be seen from the 1 Arichandra point of view, 2 Arichandra point of view, 4 Arichandra. 6 irrational, etc. Of course, here it's a little bit more complicated because we are working on Q of zeta 3. So there is zeta, I mean, the 6 cyclotomic polynomial decomposes into 2 polynomials on this field. So we have 2 different series corresponding to the two components of the phi 6. So it's phi 6 prime and phi 6 second, but everything occurs, everything agrees. So these tables are combined that way. Now let me quickly come back to the Fourier series. Remember the Fourier matrices. Remember the Fourier matrices of G4 which I wrote. Well, some of the properties which were noted by Lustig about these Fourier matrices are very striking, very strange, and in a sense not explained, except by, let me quote them, and it would please John Thomson and others, because first of all, the Fourier matrix is symmetric. Okay, very well. It has this property relative to complex conjugation, very well. S4 is 1. All right, all right. Let omega be the diagonal matrix of Frobenius eigenvalue. Remember that each unipotent character comes equipped with a well-defined root of unity corresponding to its action on the group. So let me denote by omega the diagonal matrix of Frobenius eigenvalue. Then you have this type of relations. Why? I don't know. Why? In each case, of course, we can do this, but of course, these type of connections are checked, are satisfied by all the Fourier matrices that we can construct for the special groups. I believe that you start to believe that I just cannot invent them. It's just the combinatorics is so strict that it's okay. And now, just for those who know this fusion datum, if there are some people here in the Newton Institute, there are people who know the fusion data, the physicists or theoretical physicists who know that this relation is exactly what is the kind of relation which is known with the fusion datum. Okay, never mind. Now, families and Arichandra theories, and that would be my end chapter before giving the theorem. Families and Arichandra theories. So remember that there are blocks on the Fourier matrices. In other words, there are blocks on the set of unipotent characters corresponding to blocks on the set of unipotent character shifts, which make the Fourier matrix by blocks. These are called families. Okay, so the unipotent characters is a disjoint union over the set of families of the families, but we already seen, or almost we have seen that for each choice of zeta, a root of unity, we have a zeta Arichandra theory. We can view character from the. I just did that very quickly, but for all choice of D being the order of zeta, you have a decomposition, a generalized Arichandra theory, decomposition into the irreducible of L lambda. So you have one kind of generic partition of characters here, and lots of other partitions that you can see if you look again at G4 and G2 table, you'll see all these partitions everywhere which intersect in the. So it's quite natural to ask what is the connection between the generic partition, the Lustig partition, and each of these Arichandra. Well, they must have something in common. Okay, so what are, this is what I said, what are the traces of the families over the partition defined by the Arichandra theories? And now the answer is quite interesting because Lustig, for example, has described the intersections with the principal series, simply. So the irreducible character from the split torus up to G of 1. The intersection of the families are just the Kazhdan, the families defined by the Kazhdan-Lustig basis. So it relies on this heavy machinery in Kazhdan-Lustig basis, and they are the double cells, and they are, linked with the. Okay, this is the description. In general, actually, the description, including this one, is a kind of much simpler. In general, the partition of one of the Arichandra series, which is in bijection with the set of irreducible of the cyclotomic Eck algebra. Remember, it's controlled by a cyclotomic Eck algebra, so it has a partition. It's a partition into Rouquier blocks. It's not to please Raphael that I call them Rouquier blocks, it's because he defined them. And they are just they are just blocks which are, I can just define them, it's very easy. The Rouquet blocks of a cyclotomic Hecke algebra. So this Hecke algebra is an algebra in one indeterminate, in one Woodward coefficient defined over this ring of Laurent polynomial. Just localize this ring by adding all the inverse of q to the n minus 1 and compute the blocks, Brouwer sense, primitive idempotent of the center, if you want, of this algebra of the ring. You find blocks of characters. These blocks of characters are just the traces of Lustig's family over each of these Alexandra theories. Why? Mystery. Why? It's proved, it's checked, so it's an answer. But why? I don't know. And of course, these blocks, the Rouquet blocks, are quite interesting because, roughly speaking, they are the bad primes. What counts really are the bad primes for the corresponding block, etc. All right, let me conclude by Spetz. It's a nice island, but let me conclude what we did. We call Spetz, for a special reflection group, a list of unipotent degrees, parameters of all the cyclotomic Hecke algebra, eigenvalues of Frobenius, Fourier matrices, satisfying all the above property, all the, you see, all the intricated property of all the partitions, and all these connections, etc. And many others, which I have no time to. And actually, Lustig knew a little bit of this. He knew, for example, the unipotent character degrees for Coxeter groups, which are not Weyl group. But it had not computed this, the Fourier matrix for H4, which was computed by Mahler. It's, do you remember, Raphael, how the size? It's 80 something, 84. It's 84, but huh?
60 something.
Well, it's large. It's a large matrix, and it was computed by Mahler in 94. So in a sense, it was kind of familiar for Coxeter groups that something was going on. And also, Mahler gave a solution for the imprimitive reflection groups. So namely, remember, the special ones are the G EER and G E1R. So essentially, they are the generalization of BC, because for E is 2, this is BR, and of yes, no, this is a generalization of, excuse me, of DR, because for E is 2 is DR, and these are the generalization of B and C, because for E is. Okay, so he gives the complete solution, which is kind of terrible combinatorics, but it works. And also he proposed some partial data for many primitive spatial groups. And now we can now show and produce a unique solution for all primitive spatial complex reflection group. So what's the point of such a work? The point is that to prove that there is an object behind the spatial reflection groups, definitely, which will explain all the coincidences. But be careful if you want to think of it. All these miracles are not yet explained, even for reductive groups. In a sense, Lustig has used the geometry of reductive groups to find all the marvelous property of this combinatorial datum, but there is no a priori and general explanation for this datum. So that was a talk about, I don't know, groups and non-groups, and but there was zoology, but not only zoology. Okay, thank you.
Very much, Michel. Are there any questions or comments?
But when you said that if you take a regular element in a Coxeter group, the centralizer gives a good example of a complex reflection group. But do you get many complex reflection groups that way, or
not all? Not all. Some of them escape from the. If you start from, say, a finite Coxeter group and you construct centralizers and then centralizers, etc., you don't close. You don't get the whole family of complex reflection groups.
You don't, or you do? I don't understand.
No, I do not.
You do not.
Some are not there.
And they are all spatial, or whatever the name is, or
No. If they stay not spatial by taking the centralizer. Of course, they stay spatial by parabolic subgroups, etc. Yes, but.
Maybe make another question, because I listened once to a lecture by Delis where he explained how to make the tensor category of representation of S, not Sn, but
X.
which makes me feel that maybe something like this in your case, or of course you have tried. But,
Probably there is something like this, but it's not of the, no one, people doing quantum groups think, oh, I'm interesting, but it's not this, it's something, there is a Q of X or a QW, where W, the field is larger, of X, linear monoidal category somewhere, probably, yes, which will explain, but it has to be built using these strange properties of spatial groups, which still we don't understand. I don't know. I don't know. But it's sure that there exist. I used to call this the iceberg, because we see little, and we can go little piece of the iceberg. But under the sea, there is enormous.
Oh, thank you very much.